Hello and welcome to this video about dissolving without water. We're going to look at a few ideas such as like dissolves like, polar versus nonpolar molecules, how does soap work, and something about vitamins and solubility. So, big idea here is that polarity determines which solvent will dissolve a solute or a substance. And the phrase for the day, like dissolves like. And when we're talking about like dissolves like, we're talking about whether it's polar or non-polar. Water is polar, so water dissolves polar molecules. And remember, polar molecules are molecules that have a side that is slightly negative or slightly positive. They are not the same all the way around as far as the bonds and the charges that are being shared. You can see here, these are water molecules. The reds are the oxygens, and these light colors are the hydrogen atoms within those molecules. The oxygen is more electronegative. It pulls and hogs charge, it hogs the electrons. So it's going to have a slight negative charge to it, whereas the hydrogens are going to end up being kind of deprived of those electrons a little bit, so they will have a very slight positive charge to them. And you can see how that ends up making water a polar molecule. Water easily dissolves. Other polar molecules like glucose and different sugars are very polar. You can see the oxygens here hogging some of those electrons in the bonds and creating slightly positive places where the hydrogens are bonded. Ethanol, alcohols, all alcohols are polar molecules as well because of the oxygen and hydrogen that are bonded to them. So just as polar solvents dissolve polar molecules, non-polar solvents dissolve non-polar molecules. Remember, like dissolves like. So some examples of non-polar molecules would be these long hydrocarbon chains. In this chain, these dark atoms here are carbons. The light atoms right here are hydrogens. And because this chain is even and uniform all the way around, even though the hydrogens are maybe slightly positive and the carbons would just be slightly negative, they're pulling those electrons a little more. It is even all the way around this molecule, and they're pulling evenly and distributing that charge evenly. So it is not polar, it's not sided. And so why do you think water will not dissolve oil? Well, oil would have this long hydrocarbon chain in it, and therefore it is non-polar. Water, remember, is polar. And so the polar water does not dissolve the non-polar oil. Are there molecules that have both polar and non-polar parts to them? Yes, indeed there are. Here's an example. Sodium stearate has a long chain at the end that's nonpolar. See these carbons bonded to the hydrogens all the way along this chain. And then here is our polar end. It's very ionic. It has a place here where this hydrogen actually has been lost, and so it's attracted to sodium ions. This is another way we can write this molecule. Each point, each place that this is bending is a carbon atom. Additionally, this is a carbon atom as well on the very end. This is the carbon atom right here in this non-polar, in this polar end. Here's the long hydrocarbon chain. We don't write all of the hydrogens, but we know that 2 hydrogens are coming off of each of these carbons. And this is just a very nice, simple way to write long hydrocarbon chains as well as the polar end. We could even further simplify this and make a great big circle for this polar ionic end right here. And we have, in essence, this polar head and this long hydrocarbon nonpolar tail. An example of a molecule that has a nonpolar end and a polar end would be soap. And soap forms micelles in water. And here is an example of a micelle where the head that is polar is facing out because it's interacting with the water out here. And the tails will form in toward maybe an oil droplet. So if you've got some greasy dishes, soap works really well because the little oil droplets will be surrounded by these nonpolar tails on the soap molecules, and the heads will be out dissolving in the water. And that is how soap works. It should look really familiar to you from biology. Think about cell membranes and how those are formed and what compounds make up those. So let's look at how some of these ideas about solubility and polar versus nonpolar molecules applies to vitamins. Vitamin C, this is a molecule for vitamin C. It is water soluble because it is polar. It has regions in it that are very polar here. Vitamin A, on the other hand, is nonpolar. It has this very long chain right here, the hydrocarbon chain that makes it nonpolar. So why do we care? Well, polar vitamins dissolve readily in water. And we have a lot of water in our bodies. And so the polar vitamins do not readily accumulate in tissue because any of the excess vitamin is just washed away. And for that reason, you have to replace water-soluble vitamins more quickly than non-polar vitamins. We call these fat-soluble vitamins. So you have to eat these more often. Fat-soluble vitamins, on the other hand, the non-polar kind, they do not wash away with water in your body, and so they can accumulate in your tissues. Fat-soluble vitamins can be toxic in high concentrations, so you don't want to overdose on vitamin A vitamins. Advanced ideas, what are other examples of fat-soluble vitamins, and what are their sources? Other examples of water-soluble vitamins, what are their sources? Also, how do membranes of living cells make use of compounds that have a polar end and a nonpolar end? Remember that from biology? How is this feature important for cell function? Maybe you have some other ideas too. I'll look forward to seeing what you come up with, and we'll see you in class.